You can spend months engineering a mathematically flawless machine learning model. It will achieve near-perfect accuracy during offline testing, passing every validation check. But the moment you deploy that exact same model into a live production environment, it collapses. This collapse is the result of the theory trap. It is a pervasive assumption among new data scientists that their primary value to an organization lies in hand-coding complex mathematical algorithms from scratch to prove their technical prowess. In reality, enterprise data teams do not write gradient descent or backpropagation algorithms in pure Python. They utilize highly optimized, heavily peer-reviewed open-source libraries like PyTorch or scikit-learn to handle the core math. The true challenge lies in the environment. Academic datasets are intentionally curated. They are static, pre-cleaned, and perfectly structured. But enterprise data is notoriously noisy, heavily corrupted, and structurally chaotic. A perfectly constructed mathematical equation cannot solve a business problem if the variables feeding into it are constantly shifting, breaking, or arriving in formats the equation doesn't recognize. Without rigorous systems engineering, theoretical models fail in the transition to production. To understand why these models break, we have to look at the three environmental constraints defining modern information pipelines: volume, velocity, and variety. Volume represents a massive shift in scale. We are no longer dealing with localized gigabytes of information stored on a single hard drive. By 2025, global data volume is projected to reach 175 zettabytes, driven by IoT devices and continuous digital transformation. Velocity describes how fast that data moves. Operations have definitively transitioned from overnight batch processing, where data is gathered and calculated while you sleep, to continuous sub-second data streaming, where information is processed the millisecond an event occurs. Finally, variety. The vast majority of this modern enterprise data is no longer neatly organized into relational tables with clearly defined rows and columns. The data hierarchy's massive foundational base consists of unstructured and quasi-structured formats. Quasi-structured web click streams carry format inconsistencies standard databases can't read. Unstructured data is more chaotic. Millions of daily free text delivery notes provide valuable geospatial data, but completely lack mathematical structure. Traditional databases and local coding environments buckle under the pressure of these three V's. Storing and calculating this information requires organizations to abandon old frameworks and architect entirely new, highly elastic systems. Managing this chaos requires strict professional stratification. Data engineers build the digital highways to transport the data. Data scientists build the predictive models. Machine learning engineers optimize those models to run smoothly under heavy user load. Across most enterprises, finding, cleaning, and preparing the proper data for analysis consumes up to 80% of a data scientist's daily routine. The algorithm is only a fraction of the work. To process the three V's before any machine learning can occur, teams rely on the modern cloud-native data stack. Raw data inputs flow from operational systems through a centralized, continuous pipeline. To solve the velocity problem, businesses use stream processing platforms like Apache Kafka. Instead of waiting for large, slow blocks of data to compile, Kafka ingests and routes individual event packets in real time, automating scaling and load balancing as traffic fluctuates. For volume and variety, architectures converge on the data lakehouse model. Utilizing open table formats like Apache Iceberg, this completely decouples computational processing from the underlying storage. It allows the system to flexibly absorb massive amounts of varied data while maintaining structured querying power. The final stage is reverse ETL, or extract, transform, load. This pushes analyzed data and predictive scores from the centralized warehouse back out to frontline operational tools like customer relationship management systems, enabling automated business actions. This highly elastic pipeline is the prerequisite for applied artificial intelligence. Without it, there is no reliable data, and without reliable data, predictive machine learning cannot exist. Even with a pristine pipeline, new dangers emerge. The exact moment a prototype model is deployed into the live environment, traditional software engineering failures are loud. If the code breaks, the app crashes and throws an explicit error message. Machine learning failures are silent. The code continues to run perfectly, that it generates highly inaccurate predictions that business leaders may blindly trust. The first major silent killer is data leakage. Data leakage occurs when a model is trained using information that will be unavailable at the moment of live inference. A future variable bleeds into the historical training data. For example, if a university builds a model to predict student dropouts and accidentally includes a feature variable tracking exit interview completion, the model's offline accuracy will spike to near perfect. But because an exit interview only occurs after a student drops out, that data point will be blank during live inference, rendering the prediction useless. Data leakage is an engineering and feature selection failure. It entirely bypasses the mathematical strength of the algorithm, creating a useless model that looks perfect on paper. The second silent failure is model drift. Real-world conditions constantly evolve, rendering historical training data obsolete and causing an inevitable decay in algorithmic accuracy. This happens in two distinct ways. Data drift occurs when the statistical distribution of the input features changes significantly over time. If an e-commerce recommendation engine is trained primarily on desktop web browser behavior, it will experience severe data drift if consumer habits rapidly shift to mobile application usage, which presents entirely different session durations and click patterns. The second type is concept drift. This occurs when the fundamental mathematical relationship between the input features and the target prediction variable snaps. A clear example is the onset of the global pandemic. The macroeconomic environment instantly altered global purchasing behaviors and supply chain logistics, violently breaking historical training data and rendering models trained on previous economic indicators useless. Maintaining algorithmic performance requires a continuous lifecycle of MLOps monitoring and automated retraining pipelines to prevent total model decay. Beyond engineering failures, data scientists frequently miscalibrate mathematical success against actual business utility, relying on misleading evaluation metrics. Take a highly imbalanced dataset. Imagine you are building a predictive model to identify fraudulent credit card transactions, but historically, only 1% of all transactions are actually fraudulent. If you build a rudimentary, non-intelligent model that simply labels every single transaction as not fraud, it will automatically achieve 99% overall accuracy on this dataset. It mathematically succeeds while completely failing the core business objective. To correctly map operational risk, data scientists must use a confusion matrix. This tracks true positives and true negatives, but more importantly, it isolates the exact rate of the model's errors, the false positives and false negatives. These errors carry distinct consequences. A false positive incorrectly flags a legitimate transaction as fraud, resulting in a declined card and potential customer churn. A false negative fails to detect actual fraud, resulting in direct financial theft to the institution. Overall accuracy hides these costs. Instead, highly imbalanced production systems require alternative metrics: precision, which measures the percentage of flagged items that were actually fraudulent, and recall, which measures the percentage of total actual fraud the model successfully found. Data scientists cannot simply maximize accuracy. They must actively choose whether to optimize the model for precision or recall, based entirely on the specific financial risk tolerance of the enterprise. This introduces the ultimate constraint on algorithmic deployment: behavioral economics. Consider dynamic pricing architectures, like the one used by the regional super app Gojek. They ingest massive streams of real-time telemetry, fluctuating supply, consumer demand, and precise location data to calculate optimal pricing thresholds that maximize revenue. But an algorithm cannot account for perceived pricing unfairness. Demographic data indicates that consumers, particularly Generation Z users, are acutely sensitive to user interface friction. If the dynamic pricing model aggressively spikes fares without a transparent, easily understood justification in the app's interface, it triggers immediate dissatisfaction. Users will simply close the application and defect to a competitor. This is where domain knowledge supersedes pure mathematics. A mathematically flawless, operationally efficient pricing algorithm actively destroys business value if it ignores the psychological and experiential expectations of the end user. The discipline of data science aligns mathematical predictions with human-centric business value, robust software engineering, and the realities of chaotic data environments. In the enterprise, the sandbox is just the beginning.